Share screen, desktop one, share, pin. Okay. So did you, I'm pretty sure I hit record. Yes, it's recording. Good. All right. So today I'm going to dig a little bit more deeply into some of the concepts that I've been describing by some combination of drawing and hand waving. And then we're going to start talking possibly about fractals, which will take us all of next week. But before I go there, a couple of announcements. There's a problem set due next Tuesday on Canvas. And as I told you folks, whenever I've taught this class before, I actually like Xerox the problem sets and bring them on Tuesdays. We can decide whether or not you want me to do that or whether you just want to get them off the web page for the rest of the semester. Speaking of problem sets, our wonderful course assistant, Ella, who took this course last semester, is going to be holding help hours on Mondays, which will be useful, I hope, because they're right before the homework is due. And I've gotten a room for that in the CSEL, which is the Computer Science Educational Lab, which I heard that they completely redid. I haven't been over there. Ella will also be watching a Zoom link. So if you have a quick question and you don't want to schlep in to see you can use that way. However, if there are people who arrive in person, they will be prioritized over people who join by Zoom. So just the contention there, it's too much to kind of share that kind of thing between Zoom and in person. We will be in person on Tuesday in ECCR 151. Hopefully it won't be a 1/16 of an inch of ice all over Boulder when we all have to get there. That's the usual time, which is this time. After today, I will not be using my laptop and my stupid camera to do class. I'll be using some PowerPoint, but largely the chalkboard. And so that will be the way things are offered. There will not be a remote option. There will not be a recording to post. I will be posting my slides, but as you've seen, my slides are really designed, and you'll see it even more as we go back into the classroom. My slides complement what I do on the chalkboard. They don't replace it. There are a couple of people in this class who have to miss a few classes because of conferences and travel and things like that. So please, as you get to know people in the class, be willing to take notes for other people. That's a good thing for them and it's a good thing for you. So any questions about logistics? All right. So what I'm going to do then is go back to the thought experiment that I left you with at the end of class last time, which was about stability. And I have not figured out, every time I switch from my webcam to the document camera, it undoes the focus lock button. So I apologize. I'm just going to have to wait. I haven't figured that out. All right, so we are talking about stability, and I have in my hand waving said this has to do with what happens to a perturbation. Does it grow or does it shrink? That is, a thing is stable if you make a perturbation off that thing, whatever that thing is, and that perturbation shrinks. That could be a fixed point, could be a limit cycle, could be a chaotic attractor, whatever. It's all about what happens. Stability is all about what happens to a perturbation. So thinking about a map, which is where we were with this, this mess of mathematics, there's some map F, like the logistic map. And again, it's a box of mathematics into which you throw the state of the system X at time N, and it tells you where the state of the system is going to be one time click later at N plus 1. Now, if some value X is a fixed point of that map F, that is, 0.5 is a fixed point of the logistic map or whatever, then it is the case that you throw in that value 0.5 and you get out 0.5. That's what a fixed point means. It stays there. So that means that if you stick in X star, you get out X star. That is F at X star equals X star. So that's this equation right here. Okay, so perturbation, we perturb it, we poke it. That is, we don't feed in X star, but we feed in X star plus a little bit of a perturbation. And we want to know what happens. And there are two pieces to that answer, one of which is what happens to the perturbed trajectory. That is, if I poke the pendulum and it swings back down, I could think about, well, what is the full picture doing? Or I could just think about what happens to that little perturbation. So I could be thinking about what happens to the whole thing, the whole perturbed state, or I could just focus on what happens to that delta x. In both of those situations, we start out the mathematics the same way. We take this thing that we've perturbed and we stuff it in to the left-hand side of this box, and we apply F to it, and that will tell us what happens next. And we want to know from this, and maybe iterating it a whole bunch of times, what happens to this? Again, in both of those senses of what happens. Now, this is one of those pretty abstract things where we don't know F. How can we get any traction on this? And this is where Taylor series are going to help us. So Taylor series, Taylor series help you when you know something about the height of some curve at some value x. So let me draw a curve over here. Here's a curve. At some value x star, let me make it over here, make it interesting. Here's x star. We know something about this. And then we push x star over this way a little bit. Here's this delta x. And we want to know what the height of the curve is here. So we want to know what the height of the curve is there. And all we know is stuff about the height of the curve here. But we might also know something about the derivative there. And we might even know something about the curvature there. And that's what a Taylor series leverages to tell you an approximation of where that is. And again, the skiers in the room will understand. You have your skis standing on this point, and you can figure out an approximation of where you will be this far away by taking this slope, the slope that your skis are on, and walking out this far. That's the delta x. And that's your approximation right there. I'll put it in a color. That is the approximation that you would get for what the height of the curve will be, delta x over to the left, if you just use the first derivative. Now you can see from this picture that it's not right. And that's because the curve has slope to it. If this curve was just a line like that, there were no slope, or sorry, no curvature, then here are my skis. Okay, here are my skis. And this is the point where I know where I am. Here's the delta x. Then the Taylor series will give you the perfect answer. Okay, so this is Taylor series in drawings. Here's Taylor series in math. Where I'm going to be is the height of the curve plus the slope of the curve times the x kind of distance. So if I stop right there, that's the skis over here. But I could do better. This would have there's some f double prime of x star in here. I could factor in curvature. I could factor in the third derivative, and so on and so on and so on. But if I want the first approximation, I'm just going to use this picture right here. I skip all that. Then this is how you approximate where xn plus 1 is as a function of things you know. You know x star. You have a value for that. You could compute that, and then you multiply that by your perturbation. All right, this tells you that first piece of what happens next, which is where does the perturbed trajectory go? If we want to track just what happens to the perturbation itself without kind of thinking about the trajectory that it's hanging off of, we need to subtract off what happens to the central point. So if we just want to look at this, we need to subtract off f at x star, because that's what happens to the main trajectory. So by doing that, so this from here to here is exactly this. I've subtracted this off, and I've explicitly crossed off these two terms. That means what I'm doing is I'm doing this. I'm assuming that this is good enough. And I call that linearization because this is good enough. This is actually perfect if the system is linear. So this is where the mathematics comes from that goes along with that picture that I've drawn at you a whole bunch of times now. There's some sort of first return map, we're drawing on some sort of return map. It doesn't have to be a first return map. It's some sort of return map, x n plus, I don't know, well, let's say x n plus 1 for now. And there's that line that is xn plus 1 equals xn, although I've drawn it a little bit wrong. And then there's some curve that's map f. And the argument was that it is the slope of the blue thing where it intersects the orange thing that dictates the stability of the point. In this picture, here is x star. Okay, and here is the slope of f at x star. This is right here, if I can draw it. This is f prime at x star. Okay, this here is f at x star. So there's some pictures of all the terms in the previous thing. And this, by the way, I would take some little delta x here. And now we really have all the terms in the pictures. And this is why it is the slope of the function at the fixed point that determines the stability of that fixed point. So that's just a review of the stuff that I did quickly at the end of class on Tuesday and asked you to think about a bit. So this is the, yep, go ahead. Question? No, I guess not. Okay. All right. Here's another interesting behavior. And I'm leading up to an exploration of a weird thing that you saw in problem set 1, where the system looked like it was converging to a 3-cycle and then fell off of it. And here's a drawing to explain that. Same line, x n plus 1 equals x n. Some sort of curve. Some curve f. And look what happens if you cobweb this. Okay, so from this initial condition here, x0, the points look like they're converging to some fixed point right there. But if you keep going, you can see that the trajectory kind of rattles in there, but then it rattles out the other side. What this would look like in the time domain is something like that. Okay, so it can look like a fixed point for a long, long time. This is called a tangent kind of bifurcation, because as we've talked about with the logistic map, as you change R, this curve gets higher and lower. So the curve does that. And what that means is as you change R from this value here to this value here, and then you make R a tiny bit bigger, the F curve kisses that orange line in a tangent kind of way. That is, it raises up to the point where the orange line hits the blue curve as its tangent. And when it actually hits it, it will be a fixed point. But just before that, it does this weird stuff. It's called intermittency. Intermittency. And one of the definitions of chaos that we'll talk about relies on this type of intermittency that occurs near a tangent bifurcation. So how does this relate to what you saw in problem set 1 with that funky 3-cycle near 3.87? This is hard to draw, so I'm hopefully going to get it right without doing too much cheating. I'm going to draw in the third return map space, because the interesting behavior that we saw was a 3-cycle. And so this is the right set of glasses to plot in, or right set of axes to plot on if you're interested in something that repeats every 3 clicks. So that's why I'm choosing these axes. And here's my line. Here's where it gets hard to draw. This is not quite right, but it's close enough for our purposes. And I'm trying to make this low enough so it doesn't actually get near the line. But there is something here that's interesting. Remember, that's a fixed point of F composed with F composed with F. That is the 3 time click map. Oh, that's a P. P, P, P. That means that this point here says that whatever this value is here, you apply the map once and twice and 3 times, and you'll come back there. So it's a fixed point of the 3 time click map, which means it's a 3 cycle of F. So it's a 3 cycle, oops, CL, that's an L, of F. All right. And if you look at this right here, you see, if I can zoom in on it a little bit, I tried to draw it so that the slope of this F composed with F composed with F 3 hump thing is the slope is bigger than 1. So this is a fixed point, but it's not a stable one. All right. Now, if I raise R in the logistic map, this is going to get taller, that's going to get lower, this is going to get taller, that's going to get lower, and so on and so forth. And what's going to happen, again, if I draw it properly, same axes, I'm going to not label them for now. There's eek, oink, oink. I actually drew this one better than the one above. This is because the curves in the middle are a little bit, this is a bad drawing, but you get the idea. So look at this, beep, beep, beep. And then there's still this thing, but there the slope is too slopey, so that's not stable. Okay, so this is the situation right here, just inside a chaotic band. Okay, and PowerPoint, I'm showing you, this is where that we're looking right here. And the top plot is just below this transition, and the bottom plot is just above it. So just below that transition, we are really close. This actually should kind of go down like that, and that should go down like that, and so on. So this is really close, this is really close, and this is really close. And we change R a little bit, and they touch. So this is just below the transition here. And this one's just above. And so what you see here, by the way, these 3 things, this, and that, are all pieces of a 3 cycle. All right, but this 3 cycle, by the way, is unstable. This one's still unstable. But these guys, all of these are 3 pieces of a stable 3 cycle. That's the 3 cycle that happens right here in the bifurcation diagram, that as you turn R up a little bit. But right before that, the trajectory could rattle around in here, and it could rattle around in here, and it could rattle around in here. And that's what you guys were seeing when you saw that picture of, you know, this chaotic fuzz, and then it comes out into a 3 cycle. And then it falls off, and it's chaotic fuzz, and then it comes out for the 3 cycle. That was what was going on here, is rattle, 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 like a bee in a lampshade. It hangs out near the 3 cycle, but kind of like the previous picture I drew, it'll eventually rattle out the other side. But then, because of the gathering action, and we'll talk about that more later today, the gathering action of the map pushes it back in. It'll come back in over here. So it might go over here, but then it'll go whappity whoppity whoop, and then come back in. So it'll come back in. So if you couple your picture of the one I just moved off, the tangent bifurcation picture, with this, you will hopefully understand these veils right here. Because here, right here, the trajectory was spending a lot of time rattling around inside that, space between the hump and the line, but then it would fall off. But the fact that it spends a lot of time in there means that the trajectory ends up making a lot of tracks on the state space rare, which makes it very dense. So that's how to understand unstable periodic orbits and these veils in bifurcation diagram. All right, so what I'm going to do now is, unless there are questions about that. Any questions about that? Okay. Is dig more deeply into this notion of sensitive dependence on initial conditions. Sensitive dependence on initial conditions. I am not wanting to write all that out every time I say it in the whole semester, so that is how I'm going to write it. I will say it like this, I will write it like that. This is now a canonical dynamics course, at least in this dynamics course, abbreviation. So sensitive dependence on initial conditions, the butterfly effect, small change can have a large effect. So let's say we're thinking about this in the context of a map, and we have some initial state x0, and the butterfly flaps its wings, which causes the state to move to a different initial condition. Then you think, okay, well, where does the original initial condition go? Maybe that's where the map would go. And maybe the perturbed state would go off that way. So what we want to track is this distance. And we want to track that distance and watch how it grows with time. So this is delta 0, this is delta 1, this is delta 2. We're tracking the perturbation. And let's say there's a bunch more stuff in here. This is delta n. It is the difference between the original and perturbed state n time clicks later. And it is the case that delta n grows exponentially fast. It grows as e to the lambda n. This is time. Remember, that's time. This thing has a fancy name. It is the passcode to our lectures. It is the Lyapunov exponent. So because it's the passcode, I'm sure you know how to spell it. Now you know how to pronounce it. Don't call it Lyapunov, okay? That's kind of, maybe that's in Texas, that's right, but not here. Actually, if you're Russian, it should be Lyapunov. The accent should be there, but we abuse that in the West. We call it the Lyapunov exponent. Anyway, so however you pronounce it, what it is the exponent that parametrizes sensitive dependence on initial conditions. It tells you that the small perturbation, I've said it grows fast. Well, it grows exponentially fast, and the exponent that parameterizes that is called the Lyapunov exponent. And a positive Lyapunov exponent is a signature of chaos, but we have to be a little bit careful. I'm using the word signature, not necessary and sufficient condition, and we will talk about that a bunch. Okay, so what I'm going to do now is massage all of this into a form where we have a Lyapunov exponent on the left-hand side and deltas and x's and f's over here, where f is the thing that causes these to move. These are all clicks of the function f, the map f. So I'm going to start with expressing this a little bit more formally. Here I said it grows as. Well, how does it grow? I have to get the architecture of this sheet of paper right, because there's going to be a bunch of stuff here. So the size of delta n is equal to delta 0 times e to the lambda n. And I probably should use, these could be vectors, so I probably should use norms instead. Right, so back to my picture, here's the two ends of that. I used green. This is This is X, this is X, N, and this is, well, actually, let me write it differently. This is the map F composed with itself n times applied to the initial state. So X0 it was. Where F with n in parentheses up there is equal to F composed with F composed with F n times. That is, this is the n time click map, logistic applied, basically your code for problem set 1 with the loop set to n. This point here is the same F composed with itself n times, applied to X0 plus delta 0. That's what delta n is. That's how it works. So delta n is equal to F, I'm just writing down this minus that, F composed with itself n times the top point minus the bottom point. And I'm going to use that again, so I'm going to give it a name, equation 1. Okay. Well, actually, let me call this one 2. My apologies, because this is equation 1 that I'm going to use again. Now, if I take the log of equation 1, which basically, I'm trying to get this thing by itself on the left-hand side. So the log is the right way to untangle that from everything. If the log of that, I get, this is 1 over n times the natural log. Actually, I should say this is not a log, it's a natural log, because I've got an e, I'm going to work with a natural log that makes sense, of delta n over delta 0. I probably want to do these separately. Okay. And if I combine this with number 2, I get something that looks like this. Lambda is equal to 1 over n natural log of, this is mostly just rewriting. Okay, and some size, some norms. But take a look at this. What does this thing look like? This should look vaguely familiar because it's the first theorem of calculus. This is the definition of a derivative. Remember this vaguely? I know it's the first week of calculus and nobody pays attention, but this is the definition of a derivative if we do something. So if we do the limit of as delta 0 goes to 0, this is the derivative. Okay, so let's do that. Let's take that limit as delta goes to 0. Doing that limit, we get 1 over n natural log of, and here I can actually use just an absolute value sign. This is a slightly nasty creature right there. That's a nasty creature, but we'll get rid of it in a second. Okay, so that's the definition of the derivative of this function here at this point here, sorry, at x0. Why do I say this thing is nasty? Because it's f composed with itself n times and taken to the derivative. Well, there's something that can save us in this situation. It's called the chain rule. Which is another one of these things that we remember the name of from calculus, but we would have to go and look up, figure out how to do it. But I can figure that out. So I'm going to use the chain rule, and I'm also going to use that trick of the fact that the log of the product of some things is equal to the sum of the logs of the things. So if you take log of, AB, that's equal to log of A plus log of B. Remember that vaguely? So the log of a product of a bunch of things is equal to the sum of the log of the individual things. So I'm going to use that, and I'm going to use that. I'm going to rewrite this like so. is equal to, I'm leaving some space between the equal sign because I'm going to put something else there in a second. Same thing. This is the application of the chain rule. I think this is n-1, something like that. By the way, this definition is in 10.5 of Strogatz. If this is starting to blur in your vision, you can look at that. You can just sit back, take a screenshot of this whole page, and then go look at that. But I'm actually giving a little more interpretation because I'm telling you more about how you get from here to there than he might. Let's see, now I need a natural log in here. And I need, this is now, it's not quite so carnivorous, it's just the F at some initial condition. Okay, almost done. So I used the chain rule to get rid of that obnoxious thing, and then I used this to get rid of, to take the product of the logs that the chain rule gives me and turn it into a sum of logs. Now, I want to do one more thing, which is if the, imagine the eddy in the stream looked at from above. There's going to be some places where neighboring wood chips would come together, and there's going to be other places where neighboring wood chips will spread apart. And for chaos, for the Lyapunov exponent, for sensitive dependence on initial conditions, we actually need to take a long-term average in order to see who wins. That is, in some places, a chaotic system might compress state space. In other places, it might expand state space. And what we want to know is in the long term, not at this patch of the eddy and at this patch of the eddy, but as the wood chip traverses the whole eddy for an infinite amount of time, what would happen to those two wood chips dropped nearby if they both went for an infinite amount of time? Would they spread or would they get closer together? So that is all hand waving to say we need in here a limit as n goes to infinity. This is a long-term average. That is a long-term average. You can define what are called local Lyapunov exponents, and we'll come back to those. Those are kind of like they're just what they sound like. In this part of the attractor, the state space contracts. In this other part, it expands. So now, this idea of a small perturbation growing exponentially fast in the long term should be slightly upsetting if you think about the logistic map, because the logistic map lives on the unit interval. The logistic map just, it only takes on values between 0 and 1. So what the heck does it mean to say that you drop two nearby points in the logistic map and the distance between them will get exponentially large? How can that happen? Well, there's actually, I haven't given you the full definition of Lyapunov exponent, at least the hand waving one. There is, the full definition has a directionality to it. And what do I mean by that? What I mean is that I think about, if I'm computing a Lyapunov exponent, I think about walking along the trajectory. So I'm sitting on the wood chip as it runs around the eddy. And at every point in time, I look around me and I see, well, if I look to the right and I look to the left, is the force of the water, what would happen if I put another wood chip a little bit to my right and a little bit to my left? Would the force of the water bring those wood chips toward me, or would it push them away? In state space, that means you're walking around in state space and you're looking at the curvature of the landscape. So here's my trajectory. If I'm looking at the landscape around me and it looks like that, that means that if something pokes the trajectory, it'll roll back down to me as I walk along. If the landscape looks like that, and I'm walking along the ridge of a mountain, a little perturbation will grow away from me. So the way Lyapunov exponents are actually defined is, as you walk along the trajectory, what does the cross-sectional landscape look like in the long term? So that's the fudge or the hack or the kludge that gets around the statement on my PowerPoint slide. And we will talk more about that. I realize that's completely hand-wavy, but we will talk more about that soon. Okay. So So I'm sure that some of you have thought about the fact that all of this is smelling an awful lot like eigenvalues. Indeed, even the symbol that I'm using, lambda, smells a lot like an eigenvalue. And all of you have taken linear algebra. That's now a prereq for this course, I believe. So you know about this word. This is the German word, oops, switch the camera, Liz. This is the German word for same, same. Eigen is same. So an eigenvector, technically speaking, if you were to translate the German, means a same vector. So if you're on an eigenvector, you stay on the eigenvector. That's what the language means. And it is the case for those of you, again, this is kind of review, that, oh, by the way, in linear algebra courses, they call these things lambda. We do not do that. We reserve the term lambda for Lyapunov exponents. I will call eigenvalues S's, not lambdas, so that we distinguish. So S for eigenvalue, lambda for Lyapunov exponent. So just like an eigenvalue is associated with an eigenvector, so there's some sort of eigenvector in the space, and the eigenvalue parameterizes growth or shrinkage along that eigenvector. So here's the eigenvector. Here's the eigenvalue. Again, if you start on an eigenvector, you stay on the eigenvector. That's what eigen means. And the way you move is parameterized by the eigenvalue. Now, you probably remember that there are as many eigenvectors with associated eigenvalues as there are dimensions in your space. That's because your eigenvectors need to span your space. They need to be a basis set for your space. If you have a 2D space, like my piece of paper, there's going to be 2 of them, because that's enough to completely specify any point in this paper. If there's a 3D space, you need 3 of them. The same is true for these things. And they also parameterize growth as an e to the lambda t. The difference is that this is true. These are applicable when the system is linear, and the things along which growth happens in that way are vectors. Here, these things might be all curvy. Okay, so they are nonlinear analogs to eigenvalues. Okay, so nonlinear eigenvalues, and just like eigenvalues have associated directions, Lyapunov exponents have associated directions with air quotes, because they're not really directions, they're what are called manifolds. And a manifold is a kind of generalized term for what an eigenvector is a subset of. So a manifold is the same kind of thing. You start on a manifold, you stay on it. So these things are vectors, these things are manifolds. And that word is just code for if you start on it, you stay on it. Okay, so what I'm going to do now is, as you can see from my slide, do a linear systems review. And this is a course on nonlinear dynamics. So we're not going to use a whole lot of this, but it is going to be useful both in thinking and for use in approximations. So back to flows temporarily. Here is a 2-dimensional ODE system. Okay. Linear. Okay, so that's a 2D ODE system. It's state space, well, it's state vector. These are the state variables. So the state vector looks like X, Y. The state space is the space whose axes are the state variables. And it is the case in this particular situation that I can rewrite this whole thing like so. Let me give this thing a name. Let me call this, I don't know, Z. It's a state vector. It's called Z. Then I can rewrite this like so. It is Z dot equals A times Z, where Z is that vector, and A looks like A, B, C, D. It's a matrix, 2 by 2 matrix. Now, you cannot do this operation if the system is nonlinear, because your A will not be a matrix that has just numbers in it. If there were a sign of X here, you just couldn't do that. So that's one of the definitions of linearity versus nonlinear is if you can do this, it's linear. And you probably have memories, perhaps bad dreams, of how you compute the eigenstuff given a matrix like this. In shorthand, you take your matrix A, and you subtract off S's on the diagonal, and then you take the determinant and you set that equal to 0, right? So you do A minus S, B, C, D minus S, and you take the determinant set equals 0, figure out the S's that make that true. There'll be 2 of them, right? It's going to be a quadratic. So there'll be 2 of these things, S1 and S2, and those are the 2 roots of the equation that is the determinant of this mess is equal to 0. Let's say for gags that this one's positive and this one's negative. That'll depend on what A, B, C, and D are, of course. What that means is that there is a growing eigenvector and a shrinking eigenvector. How do you find the eigenvectors? You basically substitute back in and you find the null space with some delta in there. I'm not going to do that out even, but let's say we come up with these 2 eigenvectors. Okay. And let's say this is the one that's associated with S1. This is the one that we got by messing with the null space of S2. Oh, I forgot to mention, there's a fixed point right here. There's a fixed point at the origin. If you plugged in X, Y equals 0, 0 into your box of mathematics, that's the box of mathematics, what you would get out is X dot Y dot equals 0, 0. Now look at that. That says that X dot 0, Y dot 0, that says that X doesn't change and Y doesn't change. That says that at this point, if you start at this point, nothing changes. That's a fixed point. So this is a fixed point of this system. Okay. All right. So I start on this point, start on this eigenvector. By definition, I'll stay on that eigenvector. But which way will I go? Well, here's the answer to that. This distance right here is going to change as e to the S1t, and S1's positive, so I'm going to go that way. Similarly, if I start right here, well, this distance right here is going to grow or shrink as e to the S2t. S2 is negative, so that one goes in, and this goes in, and that goes out. All right, so we know what happens if we start on one of these lines. What happens if we start off of it? Well, we start here, we'll get pulled in, and then we'll go out this way. Similar here, pulled in, go out that way, pulled in, go out that way. And these curves are hyperbolas. Hyperbolas. And for that reason, this is called either a hyperbolic, well, it's called a hyperbolic fixed point. It's also known as a saddle point. And you can think about that pretty easily because this looks just like a saddle. So let me figure this out. Okay, here's the horse's head. Okay, here's the horse's spine. Here's the horse's tail. And this is a funny shaped horse, but this is the girth, you know, the thing that they fasten the saddle on with. So that's why this is called a saddle point. And you can quite effectively think about the trajectories in state space around this, on this landscape by thinking about the landscape of a saddle and thinking about, well, what happens if I take a marble on the saddle and I send it that way? Well, it's going to roll down the spine, but then it's going to roll down the girth. Okay. So that was, this was probably, sorry, this was probably that picture or this stack of mathematics was probably a week or a week and a half in your linear systems class. So if you're feeling kind of like the wind is blowing very fast in your face, that's okay. Again, I'm not going to ask you to reproduce this on a final exam. It's just to bring you up to speed with some of the stuff that we're going to use. And the thing to really take away from this picture, I should use the other camera, is that notion of the shape of the landscape. There's a state space, that's what I was drawing in, but there's slopes and there's landscapes. And if it was a big bowl, what would happen? If it was a mountaintop, what was happen? If it's a saddle, what would happen? And those are all really useful ways to think about dynamical systems. The difference between linear systems and nonlinear systems is that in nonlinear systems, the horse can develop sciatica. So these things can start to curve in funny ways, right? So in a linear system, there's not these vectors that define the landscape. And that makes sense. So in a linear landscape, you can have a beautiful hemispherical bowl, or you can have a saddle, or you can have you can turn your bowl upside down and have a lump. That's really all that can happen. In a nonlinear system, things can get really complicated, and the landscape can have, like, think about this as like, this is the stream bed in a mountain range, and this is the ridge in a mountain range. Mountain ranges that are linear are really boring. They're all kind of, they're in lockstep. They're, like this. But real mountain ranges, this can curve. And that's what the extension is to nonlinear systems. So these green things are nonlinear extensions. And it is the case that these things here, growth along these things, these are the manifolds, and growth along these things is parameterized by the Lyapunov exponents. So a point put down here will move that away as e to the lambda, well, this is 2, this is 1. We'll move that away as e to the lambda 2t. And it is the case that these manifolds, this is what's called the stable manifold and the unstable manifold, just like the stable and unstable eigenvector. The stable manifold is locally tangent to the stable eigenvector at the fixed point. That will all come back. There's something, by the way, called the spiral theory of learning. It's just like an upward spiral. And I try to structure my courses that way. So we'll touch something and then we'll go someplace else. And then we'll come back and we'll touch it again more deeply. And then we'll come back and we'll touch it again more deeply. So that picture with these things and the curvy things, that's going to come back. So you don't need to grok the whole thing right now. It will come back. But before it comes back, I wanted to build on it a little bit and make at least write down on my slides a little bit more about what I wanted to get across with Lyapunov exponents. They are kind of like nonlinear eigenvalues in the sense of they parameterize growth along an eigen-ish thing, but it curves. Just like eigenvalues and eigenvectors, there are n of these things. That's just because you need that many directions to span a space, whether you're using vectors or you're using curvy things, you need n of them. The biggest one dominates in the long term. And that makes sense just if you think about e to the 2t plus e to the 3t plus e to the negative 2t plus e to the 46t, and you take the limit of that as t goes to infinity, they're all going to fall off the limit except for that one with the e to the 46t. So the biggest one wins. And that's something that's important in chaos theory because we talk about the Lyapunov exponent. We're always talking about the biggest one. And again, I will come back to that. I'm leaving lots of forward pointers, but I promise I'll fill them in. The third bullet is actually important. I said that you can't have attractors unless you have dissipation, because the state, something needs to be smushing the state space down. Going back to this picture of the basin of attraction with the attractor down in the bottom of it, and the thought experiment of sprinkling initial conditions all the way through the basin, taking raindrops and putting a raindrop down at every place to the east of the divide, and then tracking them over time, tracking that whole flock of raindrops. If that's like a flock of birds, if you watch that flock of raindrops, they would slowly contract onto the attractor. They might not contract like this. They might do something like this. They might do something weird, but they start out here and they end up down on the attractor. That can only happen if there's dissipation. How that connects to Lyapunov exponents, it says that basically shrinking has to win, okay? So shrinking has to win. The Lyapunov exponents that cause shrinking have to outweigh, have to out push the ones that cause the stretching. Going back to the eddy, you have places in the eddy where the water kind of brings wood chips together. You have other places where it brings them apart. If you have, if the eddy is to shrink, then the pulling together has to be in some sense stronger than the pushing apart. And that manifests as this equation that says that the sum of the Lyapunov exponents has to be negative in dissipative systems. And that is directly tied to this notion of contraction of state space under the influence of the dynamics, which is what I'm thinking about when I talk about sprinkling points and watching them go. Then the last point down there at the bottom. Remember that long-term average in the definition. Lyapunov exponents are properties of attractors. They are not, again, back to the eddy, there might be some transient where things are going apart and going together and going apart and going together, but what happens in the long term? What happens as that t goes to infinity or that n goes to infinity and the trajectory has gotten down to the attractor and it is staying on the attractor, whether it's a point, a limit cycle, a quasi-periodic orbit, or a strange attractor, the trajectory eventually gets there and stays there. So the Lyapunov exponents are associated with attractors, which means that they're the same for all initial conditions in the basin of attraction of that attractor. And the rationale is simply that for any initial condition in the basin of attraction of an attractor, the time going forward brings the trajectory down to the attractor. So no matter where you start, you end up at the attractor. Now, if something bumps you over the continental divide to the basin of a different attractor, all bets are off, and you will be governed by the Lyapunov exponents of that attractor. So this probably sounds a little bit combination of like confusing and useless, but it actually matters, as we'll see. And to drive that home, I want to do a couple of thought experiments. And the first one is, imagine a two-dimensional system with a fixed point attractor. What can we intuit from that information? Well, the first thing is, and when we're in the classroom, I'll actually stop and ask you, but it's too hard to track all the screens and stuff. So my apologies for having this be a write-only lecture for the first 2 weeks. It'll get better. The 2D business, this thing here says that there's two of them. There's two Lyapunov exponents for this system. This word right here says that the sum of them has to be less than 0. Okay. This thing here, these two words right here tell you something more, which is that if it's a fixed point, that means that any kind of extent that the system has in this direction has to shrink, and any extent that the system has in this direction has to shrink. So if I take, here's my fixed point, if I move away from it in this direction, that stuff, that perturbation will shrink. If I move away from it in any direction, the perturbation will shrink. So there's there's a basis set of two vectors that define that. So that means that the two Lyapunov exponents are both shrinky ones. So in this situation, a 2D system with a fixed point attractor, any kind of perturbation in any direction shrinks. That means that all of the Lyapunov exponents, in this case, both, are negative. So what to write down for this slide is basically shrinkage in all directions to a fixed point. Therefore, all the Lyapunov exponents are negative. And all is 2 because the system has 2 dimensions. Let's make things a little more interesting. And I'll go to my, hopefully my Zoom camera. Things a little more interesting. We have a 2D system. So that says that there's a lambda 1 and a lambda 2. Okay. That's what that says. This says that the sum of the lambda i's is less than 0. That's what we know from that. What do we know from this? Well, think about what a limit cycle looks like. That's what a limit cycle looks like in state space. And think about what happens if I perturb off the limit cycle. So I perturb, I'm here and I move over here. Well, it's a limit cycle attractor, so that means that this initial condition will roll back down to the limit cycle. Similarly, if I perturb off here, it might do something weird, but it'll roll back down to the limit cycle. If I perturb inwards, it'll roll back out to the limit cycle. So these are all trajectories of this dynamical system that are relaxing to this attractor. This circular thing is the attractor. That's the limit cycle attractor. Now here, the way to think about direction gets kind of hairy, because here, the right way to think about direction is either crosswise. This is a crosswise kind of direction. And there's an along kind of direction. So this is the along kind of direction, which is right along the limit cycle. So there's a perpendicular kind of direction, and there's kind of a parallel direction. And these are directions I'll put quotes there, relative to the attractor. Okay. And the way to think about the Lyapunov exponents in this situation, let's do the easy one first. Say I'm here and I perturb myself directly forward along that orange curve. Well, what happens to this distance right here? Depends. If the period of oscillation of the limit cycle is p, then p seconds later, this point will be here again, and this point will be here again, right? Because this one will have gone once around, this one will have gone once around. So that means that this distance is not going to grow. Now, these 2 points might spread further apart. They might spread further apart as they go around, then get together and then spread. But once they get back here, they're the same spacing. So that means that the orange Lyapunov exponent, the kind of along the direction Lyapunov exponent, is equal to 0, because this distance doesn't grow. So if it doesn't grow, no matter what time is, e to the lambda t, lambda 0. So that's the easy one. To think about the other one actually acts on this crosswise direction. So this is the transverse Lyapunov exponent goes back to that other kind of thought picture that I gave you, which is you're walking along the trajectory and you're looking at the landscape around you, and you're looking, well, does it slope down like that, or does it slope up like that? Am I walking across the top of a sausage, or am I walking through a valley? And so if it is the case that I'm walking across the top of a sausage, then if I were to drop a ball next to me, that ball would go out. If I were walking through a valley, then if I put a ball out here, it would come back towards me. That's the direction. So this is part of why I put quotes on directions, is that there is a Lyapunov exponent that is along the attractor, and then there's a transverse or a kind of crosswise Lyapunov exponent. And that Lyapunov exponent we can actually figure out just by looking at this picture and this picture, and this picture. What happens always, everywhere, if I perturb off this limit cycle, it gets pushed back. So that means that it's always like this. It's never like that. That is, I'm walking, it's hard to, let me actually switch the camera if I can. This requires hand waving. Always the case that I'm walking down something like this. It's not the case that I'm walking down something like this, because all around that limit cycle, imagine this thing here curving around. Okay, I should like one of those toys that cats have where there's the ball and it's in a groove. That's what the limit cycle looks like. And always, if the ball gets off a little bit, it'll get pushed back down by this landscape. So this is the transverse Lyapunov exponent, and it is negative. It is less than 0, which is a darn good thing because we have one that's 0 and we know that's true. So that had to be true, but it's more fun to think about it geometrically. Okay, so again, Lyapunov exponents are these parameters that kind of quantify sensitive dependence on initial conditions. Positive Lyapunov exponent, excuse me, signature of chaos, not proof. We'll come back to that. It's fairly easy to calculate Lyapunov exponents from maps. From flows, it's a little harder. From data, it's quite interesting, and you will tangle with that in problem set 9. Yeah, so that's where we're going. But one more thought experiment before we leave this. Bunch more words, each of which tells us something if we're playing Sherlock Holmes about these Lyapunov exponents. First of all, there's 3 of them: lambda 1, lambda 2, and lambda 3. That's what this tells me. We have a convention in the field of numbering them from biggest to smallest. When I say biggest, I mean that the one that's closest to positive infinity is lambda 1, the one that's closest to negative infinity is lambda 3. So this tells us that. This tells us that their sum is less than 0. This tells us that one of them, at least, and certainly it is the case that that one is positive. Oops, I should just say lambda 1 greater than 0. Okay. So we got one of them at least partially pinned down. And if you combine these two things, that tells you something. That tells you that at least one of them has to be negative in order to balance this guy out, because the sum has to be less than 0. So that's a combination of, yeah, that's this and that tells you this. And now there's actually a subtlety to figuring out the second one and deriving the last little bit of information, which is that it is the case that there's the third Lyapunov exponent is equal to 0. And what's going on here? This is akin to saying that growth along the attractor is sub-exponential. And there's a wonderful color plate in Strogatz that demonstrates this. He has this blue attractor with red points sprinkled on it, and they're sprinkled. So here's the blue attractor, and he has a whole bunch of little red points sprinkled on it. He's got 10,000 points right there. And he lets time go forward, and he shows you that these things spread out all on the attractor, but the rate at which they spread, it falls short of exponential. Now, I'm just asserting this. We don't have the math yet for me to prove it. I will return to this later on in the semester. But it is the case that and it goes back to that limit cycle thing, if you're kind of, if you're looking down the trajectory, like the pen is the trajectory, and you perturb yourself directly forward or backward on the pen, that distance will grow, but it won't grow exponentially fast. Again, I'm just asserting that for now. So knowing this, there's one more little bit of information that we can extract from these words about these exponents, which is that the magnitude of lambda 3 has to be bigger than the magnitude of lambda 1 for this to be true, if this is true. So these two things combined tell you that. And now I think we've squeezed as much information as we can out of those 5 words: 3D system with chaotic attractor. Okay, and this is going to come up, all this structure is going to come up later in one of the very last lectures of the semester when we talk about control of chaos, because systems that have this kind of eigenstructure locally are controllable. And that was one of the huge contributions of the control of chaos field. So where does sensitive dependence come from? It comes from the action of the map or the dynamics on the state space. And this is a weird thing that we do in the field, is we think about the dynamics, the F, the map, or whatever. We think about it as actually acting on the state space. We think about the map as squishing the state space. So imagine, this is really hard to do, but imagine the logistic map and this business of cobweb plots. So what that's doing is it's taking one point in the unit interval, bouncing it off the curve, and then bouncing it off the main diagonal. Well, imagine doing that to the whole unit interval. Whole unit interval, take this up, we bounce it off the curve, and then we bounce it over the line, and then we bounce it back down. So it's very hard to visualize, but that's what the map is doing. It's taking the unit interval and it's going like that. Easier to think about in 2D. So imagine the following manipulation. You have a square, you stretch it long and thin, same volumes, and then you fold it over on itself like that. Okay. And think about these 2 points, which started out pretty far apart, but end up really close together. And think about these 2 points. That doesn't show up. These 2 points that start out close together and end up really far apart. Okay. So this map actually tells you something about why people need dough. Okay, why do people need dough? They take a ball of dough and they squish it out, and then they fold it, and then they gather it together, and they repeat that over and over and over again. That's because that has a very powerful mixing effect on the solid mechanics of the dough. And it's a canonical thing in dynamical systems. It's called Smale's horseshoe map. And it is mentioned in every textbook as, well, what happens if you need dough? And so one of the people in this class, maybe about 10 years ago, decided that that was going to be her final project. Okay. And so she did the following experiment. She took a little bit of dye and she put it in bread dough and she kneaded it a few times, and she observed, that the dye ended up spread through the whole bulk of the dough. And she did some really interesting work with tracking this. She used colored beads and a camera, and I can show you the poster that came with that. So this is really fun. And I wanted to use this as an opportunity to pop up a few levels and talk about projects in this course. And I will bring a handout on Tuesday about this. The project for people is required for people in 5446. It takes the place of the last 3 problem sets. It will take, it will occupy all your time for this course for all of April and a bit of March. And it's a little baby thesis. And theses are hard. And the hardest part of a thesis is actually picking the problem. So how to think about that? I said it's a baby one. The first thing you should be thinking about is, as concepts fly by in this course, do any of them kind of pick up your ears? And if they do, that's a good place to be thinking about a project. It could be something that is apropos of your thesis, your own research. That's fine. That's called the Good Bunny Project. You can also do something completely wild and crazy like this, as long as there's interesting dynamics in it. So the first thing to do again is to be thinking, to observe as things go by, what's interesting, and in the reading too, and in the problem sets. And be thinking about, I'd like to do a project in this area. Then there's a whole bunch of other stages. So identification of the problem, background research, scoping it, carrying it out, reporting on it. And I have milestones set up in the course to help you with all those steps. So this is not like, a full-on PhD thesis. There's help with all the steps, and it's much more small. And it's far less carnivorous than a PhD thesis. So again, it can be something wild and crazy, like I want some, well, okay, there's this needing and people talk about dough, I'm just going to do something like that. But your choice, it's your project, but there is subject to an approval process. And one of the things in that approval process that I'll try to help you do is pick something that's not going to take, 10 years, but rather is reasonable to fit in 3 or 4 weeks. Okay, so stretching and folding, that map that I drew for you has a name. It's called Smale's Horseshoe. And we will use that much later in the course to actually prove that systems are chaotic. So if a system does this to its state space, that's part of a proof that it is chaotic, which is pretty cool. And what I'm going to end with today, there'll be one more tiny bit of maps on Tuesday, and then we'll dive into fractals. So my outline slide was a lie. We didn't get that far. That's okay. Last Thursday, we quantized time. That is, we started the course with people moving in a dance club, and then we made time discrete. That is, we put a strobe light on them. So we didn't know where they were at all times. We just knew click, click, click. Well, we can also quantize space. Okay, we can also quantize space. And that brings us to something called symbol dynamics. Okay, symbol dynamics. For the logistic map, lives on the unit interval, and the numbers that you got for your experiments, 0.537, whatever. Maybe it was X1 was 0.697, whatever. So these are numbers. These are nominally real numbers. But we could also divide this in half, call that A, call that B. And instead of describing the path of the iterates with these kinds of numbers, we could describe it as A, B, 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 A, B, and so on and so forth. So we could make a very highly quantized representation of the state space and describe the trajectory in this symbol space. Now, this is probably bothering you because you're saying, well, wait a minute, that's really coarse grained. How can it possibly have the same amount of information? The reason it's important, well, there's a lot of reasons it's important. In this class, one of the reasons this is important is computers do this, right? Computers do not. So computer arithmetic takes the number line and divides it up into little chunks. Machine epsilon. Okay, and all the numbers in this little chunk are called the symbol 1.739. They're all these numbers, which are between 1.7 and 1.74 or whatever, they're all mapped to that thing, which is really just a symbol. Now, those of you who know floating point, this is not exactly how it works. Just for the purposes of explanation, though, this is a useful explanation. So what's really amazing is that, and I'll end with this, this is almost as good a description of the dynamics as the trajectory in real number space, which is quite remarkable. There are some caveats, but you can prove almost all the same theorems about dynamics represented this way as you can about dynamics represented this way, which again is a darn good thing because we, in using computers, are doing this even if we don't think we are. So I will finish next time. I will talk about, I'll tell you one more story about maps and angry Russian physicists. And I will see you then in the classroom, right? Yay. So let me stop the recording so that people can ask questions.
Yeah, I had a quick question.
It's like I gotta stop.
Sorry.